This is ELC111, Intro to Electricity, and this presentation is an introduction to filters. Now, a filter is a circuit that's designed to pass selected frequencies to a load and block other frequencies from passing to the load. And we see a simple diagram of a filter circuit in Figure 1. And this diagram is really a mixture of what is termed a block diagram and what is termed a schematic diagram. If you'll note in Figure 1 that the filter is represented simply with a rectangle here with the word filter in it. And in illustrating or representing circuits, quite often we will use blocks like this so that we don't have to draw more complex circuits with components in them. We just represent this portion of the circuit with a rectangle or a block with the word filter inside of it. Now, our filters are classified as being either low pass, high pass, band pass, or band stop filters. And a band stop filter is sometimes referred to as a band reject filter. Now, in the next slide, we'll look at the frequency response of these filters. And the frequency response is just the terminology we use when we graphically represent the output, either power, voltage, or current, as a function of frequency. So in Figure 2, we see the frequency response of a low-pass filter. Again, the x-axis is frequency. Frequency is the independent variable. Load power is the y-axis. That is the dependent variable. So the load power changes as a function of frequency. And we can see from the plot of Figure 2 that at low frequencies, the load power is high, and at high frequencies, the load power is minimal. So this graphically represents the fact that at low frequencies, the low frequency AC signals are passed to the load, and the high frequency AC signals are blocked from getting to the load. Figure 3, we see the frequency response curve for a high pass filter. Again, frequency is the x-axis, load power is the y-axis, and you can see from the plot that at low frequencies, the load power is minimal, and at high frequencies, the load power is maximum. Again, the high pass filter, we pass high frequencies to the load and block low frequencies. Figure 4 shows us the frequency response curves of a band pass filter. And with this filter, we pass a selected band of frequencies. This is referred to as the mid band to the load, and we block the low frequencies and we block the high frequencies. And finally, in Figure 5, we see the frequency response of a band stop filter. And a selected band of frequencies are prevented from getting to the load. The frequencies below and above that selected band of frequencies are allowed to pass to the load. Now let's look at an example of filter circuit or filter circuits. So we see in Figure 6 an audio amplifier, and the audio amplifier outputs AC signals ranging from 20 Hertz to 20 kHz. This is the range of frequencies that are perceivable by the human ear. And with an audio system, it's difficult for one single speaker to reproduce audio signals ranging all the way from 20 Hertz to 20 kHz. So as we see in Figure 6, it's quite often we will construct what's called a three-way speaker system. And in the three-way speaker system, we have three speakers. We have the woofer, which is effective at reproducing audio energy or audible energy from electricity at frequencies ranging from 20 hertz to 2 kHz. The mid-range speaker is most efficient or effective at reproducing or creating sound energy in frequencies ranging from 500 hertz to 4 kHz. And the tweeter is best at reproducing high frequency signals from 2 kHz to 20 kHz. And part of the idea here is that, the woofer, the bass speaker in our speaker system, it could be as large as 15 inches in diameter, and it could weigh 15 pounds. And it's virtually impossible to get that large of a coil to move in and out 20,000 times a second. So with our three-way speaker system, we need to have a low pass filter in series with the woofer, so we can pass only the low frequencies to the woofer and block the high frequencies. We need a band pass filter in series with the mid-range speaker, so we can block the low frequencies and block the high frequencies, only allowing frequencies ranging from 500 hertz to 4 kHz to pass through to the mid-range. And of course, we need a high pass filter in series with the tweeter to allow only frequencies above 2 kHz to pass to the tweeter. So this is an example of an application for filters. Now, when discussing and I guess quantifying, classifying, no, not classifying, but quantifying filter circuits, one of our metrics, or one of our most commonly used metrics, is the cutoff frequency. And cutoff frequency is symbolized with F subscript C, F sub C, and the cutoff frequency is the frequency where the AC signal is considered to be filtered out. The cutoff frequency is the frequency where the output power decreases to 1/2 of the maximum output power. And this point, FC, is also called the half power point. Now, output power is quite often expressed in decibels. So if we take the and our formula for decibels, again, is dB equals 10 times the log of P out over P out max. And 10 times the log of 1/2 equals -3 dB. So the cutoff frequency is also referred to as the -3 dB point. Now, the cutoff frequency is also the frequency where the output power reduces to 70.7% of the maximum output voltage. And of course, we can express voltage ratios in decibels also. So the output voltage expressed in decibels would be 20 times the log of V out over V out max. And if we take 20 times the log of 0.707, we get -3 dB. So it doesn't matter if we're describing the output in terms of power or in terms of voltage, the -3 dB point is the cutoff point, or the cutoff frequency for the circuit. Now let's look at a low pass filter. Referring to figure 7, we see that we have, again, a low pass filter just represented with a block, and this low pass filter has a cutoff frequency of 2 kHz. And looking in figure 8, we see a graph that shows us the output power as a function of frequency. And notice the cutoff frequency, 2 kHz, is the point where the output drops to 1/2 of the maximum output power, which is 10 milliwatts. So at 2 kHz, the output has decreased to 5 milliwatts, which is half of the maximum output power. Now, figure 9 shows us a plot of the load voltage as a function of frequency. And again, the cutoff frequency of the circuit is 2 kHz, and at 2 kHz, the output has dropped to 70.7% of the maximum output voltage, which is 1 volt. So we can see graphically that it doesn't matter whether we look at power, load power as a function of frequency, or load voltage. The cutoff frequency is the half power point. It's the point where the load voltage drops to 70.7% of the maximum. Now, one of the problems with the plots that we see in figure 8 and figure 9 is that it's very difficult to predict the output or load power or load voltage from these graphs. And it's because of the fact that these graphs are so non-linear. And part of the issue is that the x-axis is what's called a linear axis. And what that means is that on the graph, the distance from 0 to 2K is the same distance as from 2K to 4K. It's the same distance as from 4K to 6K, and the same distance as from 6K to 8K. In other words, this is a linear scale like we would have on a normal piece of graph paper. So we see in figure 10 that same low pass filter plot, except now the x-axis is a logarithmic scale. What this means is that the distance from 10 to 100 is the same distance as from 100 to 1000, which is the same distance from 1000 to 10,000. This is what's called a logarithmic scale. And by plotting the output voltage as a function of frequency with frequency on a logarithmic scale, is that we've expanded all the data points down here, and we've compressed all the data points up here. So this makes our graph appear a little more linear, or much more linear, but and it makes it easier to predict the output voltage at a particular frequency. However, looking at the plot of figure 10, we can see that it's still very nonlinear up here around 10,000 or from about 5,000 to about 20,000. So we improve this by using what's called a Bode plot. A Bode plot is shown in, or the Bode plot for that low pass filter is shown in figure 11. And with the Bode plot, the x-axis is plotted on a linear scale, as we saw in figure 10. However, the y-axis is plotted in, or expressed in, decibels. And you recall, of course, that the decibel is a logarithmic relationship. So by plotting the response of this low pass filter using the Bode plot, note how much more linear the response of this filter is from around 5 kHz up to 20 kHz. And with this improved linearity, it makes it much easier to predict the output voltage at a particular frequency. Now, one thing about the filters that we'll look at here, the low pass and high pass filters, is the roll off of the filter. And the roll off is simply the term we use to describe the slope of this graph at points above the cutoff frequency. So the roll off is the slope of this graph above FC. Now, for the low pass and high pass filters that we're looking at, the roll off is stated as being negative 6 dB per octave. And an octave, you recall, is a change in frequency of a factor of 2. So an octave is a doubling of frequency or a halving of frequency. And the roll off of these filters is also stated to be negative 20 dB per decade. And a decade is a change in frequency of a factor of 10, either times 10 or divided by 10. So looking at the graph in figure 12, we see that at FC times 2, the cutoff frequency times 2, which would be 4 kHz, the output has dropped to 9 decibels. Again, at the cutoff frequency, the output has already dropped to negative 3 decibels, but from the cutoff frequency to the cutoff frequency times 2, we have dropped another 6 decibels, which puts us at a level here all the way down to negative 9 decibels. From FC times 2 to FC times 4, the output has dropped by another 6 decibels, which puts us from up here down to negative 15 decibels. Now, from the cutoff frequency to the cutoff frequency times 10, the signal drops by 20 decibels. But from up here, that's a drop of 23 decibels. So by using these stated roll-off values, I can determine the output at an octave or 2 octaves or 3 or 4 octaves above the cutoff frequency, and I can determine the output at frequencies at decades above the cutoff frequency. So this is one of the advantages of using the Bode plot, is that we can predict the output voltage at frequencies which are, of course, octaves or decades above, or in the case of a high pass filter, below the cutoff frequency. So let's look at a high pass filter circuit and its response. So we see a high pass filter in the circuit of figure 13, input voltage of 1 volt. It's stated to have a cutoff frequency of 2 kHz. And again, the plot that shows us load power as a function of frequency is shown in figure 14. And we can see that at the cutoff frequency, 2 kHz, the output has dropped to 1/2 of the maximum load power, which would be 5 milliwatts. And in figure 15, we see the plot that shows us load voltage as a function of frequency. And again, at the cutoff frequency, the output voltage has dropped to 70.7% of the maximum, which is 1 volt. Now, like we had or saw with the low pass filter, with these plots in figure 14 and figure 15, it's very difficult to predict the output because the x-axis is a linear scale. Again, down here, it's really hard to predict what the output will be at a selected frequency, either for power or voltage. So, like we did with the low pass filter, if I plot the output with frequency on a logarithmic scale, note that we're expanding the data points down here in the lower portion of the graph, and I'm compressing the data points up here above the cutoff frequency. And with this plot, it's much easier to see that, or predict or see what the filter's doing. But just like we saw with the low pass filter, we can improve this graph by making a Bode plot. And again, the Bode plot has frequency plotted on a logarithmic scale, and the output is expressed in decibels. So note, looking at the plot of figure 17, how linear this graph is in the data points below the cutoff frequency. It makes it much easier to predict the output at frequencies below the cutoff frequencies. And this plot will have the same roll-off as the low-pass filter, -6 dB per octave and -20 dB per decade. Now in figure 18, we see a band pass filter. And note, referring to the frequency response curves, or the frequency response in figure 19, that the band pass filter has 2 cutoff frequencies, and they are called F1 and F2. F sub 0, or F naught, is the center frequency. So the center frequency is the center of the frequencies that are being passed, and again, F1 and F2 are the 2 cutoff frequencies. And when discussing these band pass filters, the frequencies between F1 and F2 are called the bandwidth. And of course, mathematically, the bandwidth is simply F2 minus F1. Now, like we saw with the previous plots of the low pass and high pass filters, referring to figure 19, that it's very difficult to predict the output voltage below F1 and of course above F2. The graph is extremely nonlinear above F2, and again, it's just sort of hard to see what's going on down here below F1. And we also note, looking at figure 19, that this graph is not symmetrical, that it appears as if it's skewed to the left. So, as with the low pass and high pass filters, we can plot this frequency response using a Bode plot. Note the x-axis is a logarithmic scale. Note the output is expressed in decibels. And looking at this plot, we can see how much more linear this response is, both below F1 and both above F2. And of course, looking at the plot of figure 20, we can see that this graph appears much more symmetrical than the graph shown in figure 19. And now let's look at the band stop filter. This band stop filter has a center frequency of 2 kHz. And just like the band pass filter, there are 2 cutoff frequencies, F1 and F2. Discussing or describing these filters, we're concerned with the bandwidth, and that is the range of frequencies between F1 and F2. This is the range of frequencies that are stopped by the filter circuit. And as with the band pass filter, it's difficult to predict what's going on below and above F2. This is so nonlinear below F1 and so nonlinear above F2, it's very difficult to predict the output voltage at a selected frequency. And also, this graph does not appear symmetrical. The distance between F1 and F0 is not the same as the distance between F0 and F2. So as we saw with the band pass filter, we can improve this graphical representation of the filter's response by using a Bode plot. The x-axis is logarithmic and the y-axis is the output in decibels. And notice how much more symmetrical this graph looks than the graph of figure 22. It's much easier now to predict the output voltage at a selected frequency. So in this presentation, we looked at filters. We saw that filters are classified in 4 major categories: low pass, high pass, band pass, and band stop. And we looked at an application of filters for an audio system with a three-way speaker system. And then we defined the cutoff frequency as the frequency where the output power is 1/2 of the maximum output power, and the output voltage, the load voltage, is 70.7% of the maximum load voltage. Then we looked at the frequency response curves of low pass, high pass, band pass, and band stop filters, and saw how the graphical representation of the filter's response was improved by plotting that response on a Bode plot. And the Bode plot is simply a plot that utilizes or plots the x-axis on a logarithmic scale, and the y-axis, the output, is expressed in decibels.